So we're just starting class with a quick try it, and then we'll talk about it. Okay, so students started to try the problem, and we were able to figure out what tangent theta was. We knew that that was opposite over adjacent. We called it from SOHCAHTOA. And then triangle A, a student had given that it was 3/2. Tangent theta is 3/2. B, tangent theta is 4.5 over 3. So a lot of times we don't like decimals in a fraction. And so let's rewrite that. How can we rewrite that without a decimal? And you want to know how that you would rewrite that fraction to get rid of that decimal? So look at how many places we need to move that decimal over in order to make it a whole number. And so this is 4.5. In order to make this a whole number, I have to move that decimal over one place. And so I know that a multiple of 10 with that number of zeros, the number of zeros are equal to the number of places I need to move it over, would get rid of that decimal. So instead of just multiplying the numerator by 10, because that would change the whole problem, I can multiply this by that fancy one. In this case, I'd write it as 10 over 10. And so if I multiply through my numerator and my denominator, 4.5 times 10 is 45. And 3 times 10 is 30. Okay, so I'm sure someone could probably tell me how to reduce that. So how can we simplify that fraction?
Divide it by 5.
Okay, so what are we dividing by 5?
The numerator and denominator.
Right, so they both have to be. So 45 divided by 5, that gives us
3 over 2.
Yeah. So basically, if we divide it by 5, you're right. The end answer is 3 over 2. But if we divide it by 5, 45 divided by 5 is 9. 30 divided by 5 is 6. And so you notice that was still could be reduced, and they both had 3 in them. So 3 goes into 9 3 times, 3 goes into 6 twice. So we have 3/2. Okay, so we want to do the same thing with C. So looking at C, the triangle for C, what is tangent theta in that case?
1.5 or then wait, 1.5 over 1.
Right, so they're always a ratio of sides. So we always want to write it as a fraction. So 1.5 over 1. But again, if we want to rewrite this so that this fraction doesn't have a decimal, has another way. So what fancy one would I have to multiply this by to get rid of that decimal? So again, 10 over 10.
Professor?
Yes.
I have a question.
Mm-hmm.
So, you know how we're dividing it by 10? If it was another number there and we had to move the decimal over 2 times, would it be 100?
Exactly. So we would multiply by 100 over 100. So it depends on how many spots you have to move that decimal, and that's the number of zeros that you're going to have after the 1. And so 1.5 times 10, that's just going to move the decimal over once. That gives us 15. And then 10 times 1 is 10. We want to reduce this. Notice they both have a 5 in common. And so 5 goes into 15 3 times, 5 goes into 10 twice.
You could have also just multiplied the fraction by 2 instead of having to do times 10 and everything. It'll be a lot simpler. Just
if I multiply the fraction by 2 over 2,
you still get
yeah, that would have worked. Yeah, definitely. So it's interesting because a lot of times, and I'll see a lot of times some students will do things differently in ways I would not have even thought about doing. And it's cool to see different ways of minds thinking. Okay, so D, what do we get? Tangent theta is?
Also 3 over 2. 6 over 2.
6 over 4, but reduces at 3 over 2. So what do you notice about all these triangles?
They're the same.
They're all the same.
Are they all the same? Because I
Well,
mean,
they're not the same, but they have the same answer.
Yeah, the
Okay.
same tangent answers.
Are they similar triangles?
Yeah, so these are similar triangles. So similar triangles are triangles that have the same angles. And so that angle theta for each piece was the same measure. And so really what I'm trying to get at is it doesn't matter the length so much of the sides, it matters what this angle is that we're looking at. We're going to find later that we're going to rewrite our similar triangles or use units, the unit circle, making our hypotenuse or a radius of 1. But that's something that we're going to look at in the future. Okay.
Unit circle. No, I was inside that.
Yay, unit circle. Lots to come soon. Okay, so I just wanted to do a little bit of a try it. We are pretty much done with 7, well, pretty much done with 7.2. There was a couple things I wanted to kind of continue or just do a couple more examples because we didn't have time to do a couple examples. The other thing I wanted to do, and so let me just kind of let's recall what we had done yesterday. So trigonometry is the ratio of sides of a triangle. And we talked about SOHCAHTOA. We said that sine was opposite over hypotenuse, right? Sine theta, we have to always put that angle in there or technically it's wrong. Cosine theta is adjacent over hypotenuse and tangent theta is opposite over hypotenuse. We then looked at the reciprocal functions. And so there was the reciprocal function of sine theta is called cosecant theta. This is 1 over sine theta. So basically it's just the reciprocal of the ratio sides of sine theta. So it would be hypotenuse over opposite. The reciprocal function for cosine theta is called secant theta. And so this is hypotenuse over adjacent. And then we had cotangent theta, which is reciprocal of tangent theta, which is hypotenuse over opposite. And when we talk about opposite and adjacent, that really depends on which angle you're looking at in the right triangle. Hypotenuse is always going to be the same side, and it's always opposite than the 90-degree angle. We also talked about that the 2 angles other than the right angle, they had to sum up to be 90 degrees. And we looked and we found that there were complementary angle theorem. And those are called actually cofunctions. So if we had a triangle here.
In the book, they've been all the right.
Okay. So technically, if we looked at this, we would have that sine of angle A. This was equal to cosine of 90 minus A, which is the same thing as cosine of B.
Excuse me, Professor.
Yes.
Should that say tangent is opposite over adjacent?
Yes, thank you. I don't know where I was getting that. Sometimes I try to go too fast or thinking ahead. Okay, so tangent theta, TOA, opposite over adjacent, O over A. And so the reciprocal is A over O. Okay, so someone wants to turn off their mic. Sometimes we get feedback. Okay, so you guys remember this? So cosine of A, this was the same thing as sine of 90 minus A, or this was the same thing as sine of angle B. tangent of A is actually equal to cotangent. Let me make sure I'm not, yeah. Of 90 minus A, which is equal to cotangent of B. And you could verify that by looking at the triangle and doing the ratios of sides. And we showed that yesterday. We also looked at the Pythagorean theorem that was helping us, that would help us find a missing side of a triangle. We looked at that tangent theta could be rewritten in terms of sine and cosine. All the trig functions other than sine and cosine, because they're sine and cosine, could be written in terms of sine and cosine. We also saw the Pythagorean identity. For trigonometry, where we saw that sine squared theta plus cosine squared theta, and it doesn't matter the order you add things. So cosine could come first, cosine squared. Sine squared theta plus cosine squared theta was equal to 1. And then we talked about it's important that you be able to recognize any form of that. So maybe getting sine squared by itself, that's the same thing as 1 minus cosine squared theta. Getting cosine squared theta by itself. There's 2 other ones that you need to recognize, and technically I don't have those memorized. So let me kind of show you how you can quickly derive those. And so how you quickly derive those other 2 Pythagorean identities, which deal with either cotangent theta, secant theta, or cosecant theta, or tangent theta. You basically derive every single term by either sine squared theta or cosine squared theta. So if we went through here and we took our original identity and we said, okay, well, sine squared theta, and because this is an equation, we can do this. Whatever we do to one side, we have to do to the other side. Let's divide everything through here by sine squared theta. And so if we do that, well, sine squared theta divided by sine squared theta, that's just equal to 1. Plus cosine squared theta over sine squared theta. Well, cosine over sine is actually your cotangent. And we can pull that, and so that square, so this is cotangent squared theta, is equal to 1 over sine squared theta. That one is the cosecant squared theta. So here's another Pythagorean identity. And so we could also see this in different forms. So if I subtracted cotangent squared theta, I'd have 1 is equal to cosecant squared theta minus cotangent squared theta. Or if I subtracted 1, I could say cotangent squared theta is the same thing as cosecant squared theta minus 1. So just, I don't know, an easy way to remember which one is cosecant and which one is sine. How I do it is I know sine and cosine, one starts with S, one starts with C. So cosecant is going to be, this one starts with C, so I know it's the reciprocal of the other one that starts with the letter S, so 1 over sine. Secant, this is the reciprocal of cosine. It starts with S, so it's 1 over the cosine. I don't know if that helps to memorize it or not, but those are things that you need to have memorized. And that's just helps me know how to do it. Okay, so one other identity that you should quickly be able to derive if you don't have it memorized is taking the original sine squared theta plus cosine squared theta equals 1. And now instead, divide everything through by cosine squared theta. So sine squared theta over cosine squared theta, that is actually tangent squared theta, plus cosine squared theta divided by cosine squared theta is 1, is equal to, and 1 over cosine squared theta, well, that is, it starts with c on the bottom, so it has to be the s, secant squared theta. Okay. And again, you also need to recognize other forms of this.
What are these forms called?
These are our, I think they're called the Pythagorean trigonometric identities, but let me just make sure. First, I'm not going to find it right where I want it. In the book, they just called them the fundamental identities. I have multiple books in here. So they're just identities. I call them kind of the Pythagorean identities, trigonometric identities, because we basically got this by looking at the Pythagorean theorem, a squared plus b squared equals c squared. And we went through and we divided everything through by a squared, and then we divided everything through by b squared, and we rewrote it because we had the ratio of sides as fractions, then we rewrote those as trig functions. So that's
Yep.
kind of why I call them the Pythagorean identities for trigonometry. Okay. Examples in now. Actually, this was kind of a cool question. So let's try it. So I'm going to have you guys try it. And you're going to use those identities that we just had. And looking at the following, which expression does not equal 1? Okay, so there's 4 expressions. We have cosine squared theta minus sine squared theta. B, we have secant squared theta minus tangent squared theta. C, we have cosecant squared theta minus cotangent squared theta. And D, we have sine squared theta plus cosine squared theta. So take a minute and tell me which one doesn't equal 1. There could be more than one, maybe. And how could you prove it? You guys work on that for a second. I'm just going to pause the video. Okay, so you guys have had time to work on it, and a little bit of feedback that we believe it's A, possibly B, if there's more than one answer, and D. So how could we do this? How did you show it? You wanna?
Well, I use the identity cosine squared plus sine squared is equal to 1. So if you subtract sine squared from cosine squared, you can't get 1.
Right. Anyone show it a different way?
I just saw that because there's like a plus sign, so the sign can't be negative, so that means A is the answer.
Right. So how would you show these other two were correct? These are all the other ones equal to 1. I mean, I guess we can see D right away, right? That one has to equal 1. How about, what if you, I'm just thinking of a different way to do it than looking at these identities, and these identities again are thinking of it as ratios of sides. If we go to secant squared theta, what do we know is the ratio of the sides there? So this is the 1 over cosine, so it's the reciprocal of what cosine is.
Hypotenuse over adjacent.
Right, so we could think of this as hypotenuse squared over adjacent squared, because of that squared there, minus, and then what do we know about tangent squared?
Opposite over adjacent.
Right, so opposite over adjacent, and because that tangent is squared, we have opposite squared over adjacent squared. And I really don't need the parentheses there. Notice those are both have the common denominator. This might be harder to do. So we have h squared minus opposite squared all over a squared. If you're thinking of your triangle, so let's say this is theta, that would mean this is adjacent, this is opposite, and this is our hypotenuse. What do we know about h squared minus our hypotenuse squared minus our opposite squared? So let's go back to the Pythagorean theorem. Usually we don't use the O and the H in there, but that's okay. We know the Pythagorean theorem says that you square each leg and sum it. So a squared plus O squared equals H squared. So if I subtract O squared on both sides, I get A squared is equal to H squared minus O squared. Notice that's our numerator. Our numerator is the same thing as A squared. You can rewrite it as that. So A squared over A squared is
1.
1. So that's another way to kind of think about it with these identities. Okay, you guys are right. The one that doesn't work, and it's just actually A. So we can kind of do the same thing with C to prove it, or we can use one of the identities to show it. Okay. But I'm not going to go through that just because of time's sake. And I want to. Okay, so if you're given a trigonometric function and what it's equal to, you should be able to find all the other trigonometric functions. So for example, if you were given the following triangle, where the leg that is vertical is 2, theta is up in the upper angle, the hypotenuse is 4. And actually, this actually wants us to find the 6 trigonometric functions at the angle theta. So find all 6 trig functions of theta. So it's the first thing that you guys would have to do in order to find all 6 of these trig functions.
Find the length of the missing leg.
Right, so we need to figure out the missing leg. And so we're going to do that by
Using the
Pythagorean
Pythagorean theorem.
right, so using the Pythagorean theorem. And so we know the hypotenuse squared, so 4 squared is equal to, what do we want to call this? I don't really like to call it O all the time because the O kind of looks like 0. Let's maybe just, and I know it's opposite of theta. I don't know, let's call it X, doesn't matter. Okay, so 4 squared is equal to X squared plus 2 squared. So we have 16 is equal to X squared plus 4.
Oh, good. The wind carried that one.
Yeah, the wind.
Subtract 4 on both sides. And so we get X squared
Yeah.
is equal to 16 minus 4,
Yes, the chair.
which is 12. Take the square root of both sides, we get X is equal to square root of 12. So you should be able to rewrite these. So if you have a factor underneath the radical, you need to pull that out. So factor of 12 is 4, square root of 4 is 2. Pull that out and we have a 3 left over underneath the radical.
Stupid question, but why wouldn't this be a plus or minus 12?
Because it's a triangle, and so the length of a side is always positive length. And so we're never looking at a distance as being negative. Later, well, we'll talk about that later. Yeah, so you don't put the plus or minus there. So why don't you guys find what is sine theta? You guys go ahead and try it. Since we've finished the triangle, find sine theta, cosine theta, tangent theta, secant theta, cosecant theta. And cotangent theta. And so when you're doing this, make sure there's no radicals left in the denominator. So I'm going to give you a couple minutes to work on that, and I'm going to pause the recording while you work.
Oh, okay.
Okay, so sine theta. Someone want to tell me what sine theta? What did you get for sine theta?
2 square root of 3 over 4.
Right. So opposite,
Sure.
sine is opposite, and so that's how you got the 2 root 3. And then over 4, because that's the hypotenuse.
Mhm.
So did you simplify that?
No, because the rational is on the numerator. Wait, what?
So we do want to still simplify this because
Oh,
note
okay.
the 2 times root 3, and then we have over 4. So 2 and 4 both have a factor or 2 that are common.
Oh, you mean like simplify?
Yes.
Yeah. Oh, yeah, I did that. Got the square root of 3 over 2. No?
Right. Good job. So square root of 3 all over 2. So just make sure you guys, when you're doing these and you're working with fractions, in the end, always reduce your fractions as far as possible. And then again, no radicals in the denominator, but the radical wasn't in the denominator there, so we're okay. So somebody else tell me what cosine theta is.
1 over 2.
1 over 2. So you got 1 over 2 by doing what?
By doing adjacent over hypotenuse?
Right, and so adjacent to theta was 2, and the hypotenuse was 4, and then you notice that it reduced, and so that's how you got 1/2.
Yes.
Good job, Alyssa. Anybody else for tangent theta?
I got square root of 3/1.
Okay, so square root of 3/1. So I don't see square root of 3 or 1 on here. So tell me how you got it from that.
All right, so tangent is opposite over adjacent, and then I got 2√3/2. And then I reduced it because there's a 2 on the top and the 2 on the bottom, and I got √3/1.
Right. Yeah. And so actually, and I said, write it as a fraction. We can keep it as this just square root of 3, but just realize if it's asking you to use that information to write a triangle, then think of it as square root of 3/1. But good job. What about secant theta? Who got that and how did you do it?
Not really sure, but isn't it no solution because you'd have a radical in the denominator?
No, you could just flip it on the top then. The
it's
answer is going to
okay.
be
It's okay to have a square root in the denominator. That means it's still a solution. It's not okay though to have 0 in the denominator. That would mean that was undefined. So someone was talking about a reciprocal maybe? Is that what I heard?
So the answer would be 2 times square root of 3/3.
Everybody agree?
Wait, what did you say?
Yeah, can you show us that one?
I believe you said 2√3/3.
Yep.
And then so I was just curious if that's what everybody else got.
Yes, I just didn't, I forgot to simplify it.
Anyone disagree with that answer?
I think maybe I did it wrong, but isn't it a 1 over cosine? So wouldn't it be the hypotenuse over adjacent
You're correct.
over 2?
Yeah. So you might have gotten confused on where I wrote it, that secant was kind of next to the sine theta, and that would be the reciprocal.
Yeah,
But
my bad. I flipped them around by accident.
yeah, and that's okay. I just want to clarify, and I kind of did that on purpose just to see if you would catch that. So secant theta is 1 over cosine theta, and so we already have what cosine theta is, and so we could just take the reciprocal. We don't even have to go over to the triangle and look at the ratio of sides. And so we can flip 1/2, the reciprocal of that, which is just 2/1 or 2. And so cosecant, that's the reciprocal of sine theta. So this is where it's a little harder. And this is where maybe not rationalizing, oh no, it wasn't rationalized before, sorry. This is a little harder because now when we take the reciprocal of sine theta, we now have a radical in the denominator. And so we have 2 all over square root of 3. So again, rationalizing the denominator, you're multiplying that by a fancy way to say 1 in order to manipulate this so that the radical falls away. I know square root, I need 2 of a factor in order for that square root to fall away. There's only 1 3 here. So if I multiply it by another √3, that gives me square root of 9. So we get 2√3 all over square root of 9, which is 3. Oops. And we can't simplify that because of the 3 is underneath the radical in the numerator, and it doesn't have a radical in the denominator. Just don't, it's hard to see this. And then cotangent theta, well, that's just the reciprocal of tangent theta. And so if I think of it as √3/1, this is 1 over √3. Same idea as one above, multiply by root 3 over 3, over root 3 over 3. And so we get square root of 3 all over square root of 9. But square root of 9 is 3. Okay, so hopefully that wasn't too bad. And if you were struggling, hopefully now that kind of clarifies what you were doing wrong and that you could go now and work with a triangle and find all 6 trig functions. Trying to see what time it is. Let me do one more example and then let's take a break. Okay, so this time you're given a trig function. So let's say you were given that secant theta is equal to 3. So use the definition or identities to find the exact value of the remaining 5 trigonometric functions of the angle theta. Okay. Okay, so I kind of went to a harder one so that we can do the easier ones. Any ideas on how you would find the 5 remaining trig functions knowing that secant theta is equal to 3?
Since secant theta is not a fraction, that means it would be h over a, and the a would be 1, and the h would be 3.
So secant theta, we could rewrite 3 as a fraction as 3 over 1. So recall, and if you don't remember what secant theta is, we can quickly derive what the ratio of the sides are. We know this is 1 over cosine theta. And so this is 1 over cosine soca adjacent over hypotenuse. Flip it, so this is the same thing as hypotenuse over adjacent. And so knowing that, we know what 2 of the sides of our triangles are. So we know the hypotenuse is equal to 3. And we know that the adjacent side of our angle theta is 1. So make a right triangle. Oops. This is not to scale. And it doesn't matter where you put theta as long as it's not where the 90 degrees is. So we know hypotenuse is across from the 90 degrees, that side, so that's 3. Again, this is not to scale. Let's put theta on the bottom left. And 1 on the bottom is our length. So in order to find the 5 remaining trigonometric functions, all we need is to figure out what that last side of the triangle, that leg, what that length is, and then we can do the ratios. And so by Pythagorean Theorem, and again, you're going to kind of get used fast at this. Because this is a leg, I know that the leg is y squared is equal to the hypotenuse squared minus the other side squared. So y squared is equal to 9 minus 1. So y squared equals 8. Take the square root of both sides. So y equals square root of 8, which simplifies as 4 times 2 underneath the radical. Square root of 4 is 2, so 2 root 2. So you should have been able to get cosine theta without even making your triangle, right? You could have just done the reciprocal of secant theta. So 3/1 is 1/3. And you would also see that now if you made your triangle. Adjacent of theta is 1, hypotenuse of theta is 3. So sine theta, so opposite, which is 2√2, all over hypotenuse, which is 3. So let's just do the reciprocal. So reciprocal function is cosecant theta of sine theta. And so this is 3√2, I'm sorry, this is 3 all over 2√2. So unfortunately, radical in the denominator, we can get rid of it by multiplying by √2 over √2. So cosecant theta is equal to 2√2 all over, well, square root of 2 times square root of 2 is square root of 4, which is 2, times this 2 out here, which is 4. Things reduce. And so 2 goes into 2 and 4, so we get √2 all over 2.
Professor, how did you get after 3/2 radical 2? How'd you get the 2 radical 2 over 4?
Okay, that had to do when I was, oops. I see where you're asking, because I wrote that 3 down here as a 2.
Okay.
So this, yep, you're right. So this should be a 3. This should be, then that changes everything, because then it wouldn't reduce.
Okay,
right?
thank you.
Thank you for catching that. Did I do everything else right?
Yeah.
Okay. So we have 3√2 all over 4. There we go. And then tangent and cotangent are the last ones. So tangent theta is opposite 1 over hypotenuse. Not hypotenuse, sorry. SOHCAHTOA, opposite over adjacent. So 2√2 all over 1, which we then can write as 2√2. And then cotangent theta, reciprocal. So 1 over 2√2. We need to get rid of the radical in the denominator. So multiply both top and bottom by √2. So we get cotangent theta. That's √2 all over. √2 times √2 is √4, which is 2. 2 times this 2 over here is 4. So √2 over 4. And so we found the 5 remaining trigonometric functions, given what one of the trigonometric functions was. So any questions on what we've kind of covered so far today? So we're going to take a break, and when we get back, we're going to go and look at the main triangles that we're going to really want to know what the ratio of sides are for particular angles, like 30 degrees, 45 degrees, and 60 degrees. And we'll do that, we'll derive how you can come up with that. So let's take about a 15-minute break. Let's meet back here at 11:20, so a little less than 15 minutes. Should pause that one. Okay, so you should be seeing my screen, special angles and triangles. We're going to derive those special angles that we need to know. So for some reason, if you don't memorize it, you can actually come back and derive it, but that would take too long. So you do want to memorize these and oops, oh shoot. Hopefully you're still there. I accidentally turned off my computer. I can hear you, so that's good. Sorry about that. So you could derive these, but you want to memorize them. You don't want to spend that time. Okay, so let's look at a equilateral triangle. An equilateral triangle is when all the angles are equal and all the sides are equal. And so let's just draw an equilateral triangle. And that looks like an equilateral triangle. And well, if we know that the sum of the three angles of a triangle has to be 180 degrees, and all the angles are the same, well, 180 divided by 3 is 60 degrees. So we know that each one of these angles in here has to be 60 degrees. So angle A equals angle B equals angle C. And same thing, side A, side B, and side C are all the same size. And we said that the angles were equal to 60 degrees. Okay, but we've only been dealing with right triangles. So let's take this and actually let's give this triangle the same size. And we saw that it didn't matter really at the beginning of class, the sides of the triangle. It was more the angle. We talked about similar triangles. And so this is 60 degrees. Let's say that this side was 2. They're equivalent. So this is 2 and this is 2. We're going to make this a right triangle and we're going to divide this triangle in half. So if that's the case, let's just look at one side of this triangle. It doesn't matter the left triangle I just created or the right one. And let's just redraw it real quick. And so we know the hypotenuse is going to be 2. Well, if I split this half down the middle and this whole length was 2, then I know that each base of each of the other triangles would have to be 1. So I know that this side, this base down here, is 1. So by a Pythagorean theorem, we could figure out what this length over here is of the leg of the triangle. So we know a hypotenuse and we know one leg. And so using the Pythagorean theorem, I know that this one leg, I'm just going to call it y. We know that y squared is equal to the hypotenuse squared, which is 2 squared, minus the other leg squared, 1 squared. So y squared is equal to 4 minus 1. So y squared equals 3. Take the square root of both sides, we get y is equal to square root of 3. Oops. Well, when we split this triangle in half, this angle down here, that lower angle on the left, is still 60 degrees. But this angle up here, before we split it was 60, but when we split it in half, so the angle up here on the top of our triangle is 30 degrees. Or we know that this remains 60 degrees. This is a right triangle. We made it a right triangle. 60 plus 90 is 150, so the remaining side has to be 30. Okay, so basically we need to know our trigonometric functions at 30 and 60 degrees. And so we can get that by looking at this. And so cosine of 60 degrees. So cosine was adjacent over hypotenuse. So looking at 60 degrees, the adjacent to the 60 degrees in this triangle is 1 all over the hypotenuse, which is 2. If I'm looking at sine of 60 degrees, Well, sine of 60. So that's opposite over hypotenuse. Opposite of the 60 degrees is the length root 3. That side, all over hypotenuse, which is 2. Tangent of 60 degrees. This is equal to opposite over adjacent. So opposite is root 3. All over adjacent, which is 1. So this is root 3. And then basically, again, if we know what cosine and sine are, we can get the other ones. It's nice to know tangent too. I'm not going to write those, the secant, cosecant, and cotangent right now. Basically, those are just the reciprocals, and we can get those pretty easily. But let's now look at 30 degrees. So if I looked at cosine of 30 degrees, there's two ways I can do this. This is a cofunction of sine of 60 degrees. So by that definition we talked about, this would have to be root 3 over 2. And let's just show it by looking at our triangle. So cosine of 30 degrees, cosine is adjacent. So the adjacent side of 30 degrees is this square root of 3. And the hypotenuse is 2. So root 3 over 2. Sine of 30 degrees, well, that's the same thing as cosine of 60. Or look at 30, opposite of 30 is 1, and hypotenuse is still 2, 1/2. Tangent of 30 degrees. I don't have cotangent here, so I can't do that, but I can look at the ratio of the sides, and tangent is opposite over adjacent. So 1 over root 3, which if you rationalize the denominator, I'm not going to do it just to save a little couple minutes, this is root 3 over 3. So like I said, if you memorize these, it's easy to, and you know the definition of cosecant and secant and cotangent, it's easy just to take the reciprocals of these and don't have to worry about memorizing all of them, but you can if you want. So the other angle that's really important to know is 45 degrees. So looking at a triangle, that's something we know that has 45 degrees. Well, if two of the angles are the same, that means actually that the sides across those angles are also equivalent. And so let's call this length 1. And so that's across from the 45 degrees, so the other leg is also 1. It's an isosceles triangle. And so we could figure out what the hypotenuse is, knowing that those two sides are the same length. And so hypotenuse squared is equal to the leg squared plus the other leg squared. So hypotenuse squared is equal to 1 plus 1, which is 2. So the hypotenuse would be square root of 2. And so looking at our 3 that we really need to memorize, cosine, sine, and tangent of 45 degrees. Well, cosine of 45, it doesn't matter which one you choose. Choose one of the 45 degrees, and that's adjacent, which is 1, over hypotenuse, which is root 2. So 1 over root 2. If we rationalize the denominator, this is going to give you root 2 over 2. Well, cosine of 45 is the same as sine of 45. which is 1 over root 2, or root 2 over 2. Tangent of 45, so it's opposite over adjacent, so 1 over 1, which is 1. Okay, so not only should you know these in terms of degrees, 30, 45, and 60 degrees, you should also recognize these when those are in terms of radians. So recall on how to convert degrees to radians. So if I'm looking at 30 degrees, that's where we were multiplying by pi over 180. And pi over 180, we can reduce that. 30 goes into 180 6 times. So this is equal to pi 6. If we were looking at 45 degrees, again, to convert this into radians, we multiplied by pi over 180. 45 goes into 180 4 times, and so radian measure of 45 degrees is pi fourths. 60 degrees, multiply by pi over 180. 60 goes into 183 times, so the radian measure is pi thirds. Okay, so basically, again, you should be able to identify these when you're looking at cosine of these measures, or any trig function of those measures. So cosine of pi 6. So sometimes students like to right away convert, and sometimes this is easier when you're doing it at first, just to convert these into degrees. But these you really should recognize. I know really quickly that 30 degrees, 30 over 180, 3 goes into 18 6 times. And so I know that's pi 6. So cosine of 30 degrees, this was root 3 over 2. Sine of, pi 6, or sine of 30 degrees is 1/2. And tangent of pi 6, this was equal to, I believe, hold on, root 3 over 3. Okay, so like I just said, hold on, let me just check. Let's say, and I did check because I knew it would be faster than doing it this way, but let's say I didn't remember tangent. As long, again, as we know sine and cosine, we can always derive the other 4 trig identities. And so remember that tangent theta was equal to sine theta over cosine theta. So technically, if I just memorize these 2 trig functions, I'm good. And so if I'm looking at tangent of pi 6, this is sine of pi 6 over cosine of pi 6. Well, if I go back up here, or I should know it, sine of pi 6 is 1/2 divided by cosine of pi 6. Well, that is root 3 over 2. If I invert multiply, because I have a fraction divided by a fraction. This is 1/2 times the reciprocal of the denominator, which is 2 over root 3. 2's cancel, I get 1 over root 3. Rationalize my denominator, I get root 3 over 3. Okay, so it takes a little bit longer if you don't have it memorized. Personally, one of the ways I remember that tangent of 30 is root 3 over 3. I know one of them is root 3, and I know one of them is root 3 over 3. 30 has a 3 in it, so it has to be the one that has the more 3's in it with the function, the ratio. So that might help you. So 60 doesn't have that 3 in it, and so it's the root, just the root 3. I don't know, sometimes you just use what helps. Okay, so that was just cosine of those 3 of pi 6. Now we want to look at that for pi thirds and pi fourths. Well, cosine of pi fourths, that was 45 degrees, which is root 2 over 2. Sine of pi fourths, that's the same thing as cosine of pi fourths, which is root 2 over 2. And tangent of pi fourths, well, if I thought of it as sine over cosine, root 2 over 2 divided by root 2 over 2 is just 1. And then pi thirds. So cosine of pi thirds, that's 60 degrees. And that is the 1/2. Sine of pi thirds is root 3 over 2. And tangent of pi thirds, which is 60 degrees, that is just root 3. Okay. So let's look at some examples. So for the following, find the exact value of each expression. Do not use a calculator. So if we had 4 times cosine of 45 degrees minus 2 sine of 45 degrees. Okay, so we're evaluating this expression. We need to use order of operations. We're looking at cosine of 45 degrees. Oops. Minus, and I'll just put a parentheses there, minus 2, and then we're looking at sine of 45 degrees. And I'll put a parentheses there. So 45 degrees, cosine is what? So root 2 over 2. And sine of 45 degrees is also root 2 over 2. So order of operations, multiplication before addition and subtraction. And so 4 times root 2 over 2, we can simplify our fraction. There's a 2 in the denominator and a 4 in the numerator. So 2 goes into 4 twice. Over in the second grouping, 2 goes into 2. So those cancel. And so we're left with 2 root 2 minus 1 root 2. So we can only combine terms with radicals if they're the exact number underneath the radical and they're the exact same index on that radical. They're both square roots. And so just add or subtract the numbers in front. So 2 minus 1, so that's 1. And then the radical they share in common, root 2. Okay. So let me give you a trick that I found that can help you memorize these trig functions. It has to do with your hand. So basically, you can use this on a test because you will have your hands on a test. We are looking at a 90-degree triangle. And so think of our hand as a 90-degree, right? Okay, so our thumb is at 0 degrees. This is at our, what we were talking about at the beginning of classes being the standard position. And maybe I should not have my share screen right now while I'm doing this. Actually, before I do that, the formula you're going to use to find these trig functions is going to be the square root of n all over 2. So this is a trick to memorize or to find your trig functions. Well, not really. Well, find sine and cosine. And remember, if we know sine and cosine, we can find the other ones.
Professor, I had a question.
Uh-huh.
What does the N stand for?
Yeah, so I haven't told you yet, but good question. Yeah, you don't even know what that it means, huh?
Yeah.
N stands for number of fingers, and it depends on if we're looking at sine or cosine. So again, we have our 90-degree angle. This is going to be 0 degrees. Remember this top, this is 90. If I'm doing a rotation, this is 0 degrees, then I'm going to have 30 degrees, 45 degrees, 60 degrees, and then 90 degrees. Well, each one of our fingers can represent a degree. So this is 0. I can move this down. It's kind of like 30 degrees, pretend. This is my 45 degrees, the one in the middle of 0 and 90. This is my 60 degrees, and this is my 90 degrees. These are all important triangles. And so it has to do with your hand, and I can't draw, but I will try. That's my pinky, my ring finger, my middle finger. Yeah, see, I can't draw. So this is 0 degrees, 30 degrees, 45 degrees, 60 degrees, and this is 90 degrees. Sorry. If you look at the alphabet, this is how I remember which way I'm going to go for my fingers. I know cosine is at the top of the alphabet and sine is at the bottom if I'm looking at alphabetical order. And so sine starts below. You're going to count the number of fingers upwards. And then cosine, which is above, you're going to count the number of fingers below, depending on which angle we're talking about. So n equals the number of fingers above or below the angle we are looking at. So n equals, oops, number of fingers above if we're looking at cosine. And n equals number of fingers below the angle we're looking at for sine. Okay, so again, the formula is going to be square root of n all over 2. Okay, so let's start at 0 degrees, which we didn't talk about. So maybe let's start with 30 degrees. We'll talk about 0 degrees later. So 30 degrees. If I look at the number of fingers above my 30 degrees, there's 1, 2, 3 fingers. So cosine of 30 degrees, there's 3 fingers above, so that's root 3 all over 2. If I look at sine of 30 degrees, oops, want the 30 there. That's the number of fingers below the 30. Well, this is 30 degrees. Below, there's only 1 finger below, so that's root 1 over 2. But the square root of 1 is just 1, so 1/2. If I look at cosine and sine of 45 degrees, no, it's the number of fingers above for cosine, number of fingers below for sine. So 45 degrees, we have 0, 30, 45 degrees is here. And so there's 2 fingers above 45 and there's 2 fingers below 45. So this would be root 2 over 2, and this is root 2 over 2. Kind of cool, huh? Cosine is 60 degrees, sine is 60 degrees. I know it's the square root of the number of fingers. So 60 degrees is here. And so there's only 1 finger to the top of that, which is 1. So that's 1. Cosine of 60 is 1/2. 60 degrees is here. So below, the number of fingers below my 60 degrees is 3. So we have the square root of 3 over 2 for sine of 60. So technically those work for 0 and 90 degrees also. So let's just do that because we're going to do it anyways. So cosine of 0 degrees. If you look at the number of fingers above my 0 degrees, there's 1, 2, 3, 4. So that would be square root of 4 over 2. Square root of 4 is 2, and 2 over 2 is 1. So cosine of 0 degrees is 1. Sine of 0 degrees. Well, sine of 0 degrees, if I look at 0 degrees, I don't have any fingers going below my 0 degrees. And so this would be the square root of 0 all over 2. Well, square root of 0 is 0. 0 over a number other than 0 is 0. And so sine of 0 degrees is 0. Well, you can use the fact that these are co-functions of one another, meaning that 90 degrees minus this would give us the other. Cosine of 90 degrees, or you can use our thing. So cosine of 90 degrees, number of fingers below is 4. So square root of 4 over 2, which is 2 over 2, which is 1. Oh, sorry. That's sine. Sine is below. So that was root 4 over 2. 2 over 2, which is 1. Cosine is the numbers above this. Well, there's nothing above this. And so its square root is 0 over 2, which is 0.
Professor, I thought sine was below.
You're right. Sine was below. Yeah. I caught that. Thank you. So I don't know if that helps. You can find some really cool things on the internet. And that was one that I found that I thought maybe could help students remember. Let's see where we're at. So I just I thought this was kind of good because this is some algebra and this is stuff that you're going to see maybe in calculus. And I'm assuming most people that are in this class are going on in mathematics, so you really need to know this stuff. Let's say that you had the following functions. So you were given that f of x, this is equal to your sine function, so sine of x. G of x, this is equal to cosine of x. H of x is equal to 2 times x. And one more function, p of x is x over 2. So it wants us to find the following. Part A, find parentheses f plus g, end your parentheses of x. So I thought this was good because they're just kind of a review of notation and function operations. So if you see this, this is basically just saying, and it's not the distributive property here, even though it kind of looks like this, but it basically is saying you're taking your function, whatever it is, of f of x, and you're adding it to your function, whatever that is, of g of x. Actually. And we wanted to figure out, okay, let's just do that. And so f of x, if we look at this, is sine of x, plus g of x, if we look at that, that's cosine of x. So if it said find f plus g of 30 degrees, so this would be the same thing as f of 30 plus the g of 30. That notation is telling us we're plugging in 30 degrees wherever we see a variable x in that expression. And so we have sine of x, so sine of 30 degrees, plus cosine of 30 degrees. So sine, that's below, here's our 30 degrees. So that's square root of 1 over 2, that's 1/2. Plus, so 30 degrees cosine, there's 3 fingers above 30 degrees, so this is root 3 over 2. We have a common denominator already, so we can sum our numerator, but they're not like terms. So we're just going to write it as a sum. So 1 plus root 3 all over 2. Let's say it had parentheses, an F, a little teeny circle in between that F, and an H of, let's say, pi thirds. Okay, so you got to remember what that little circle means. That represents the composition of two functions. And so let's just recall. So if we have f of g, actually that was an h, f of h, and let's just put the x there, of x. So basically all this is telling you to do is take your equation of h of x and plug it in wherever you see an x into f of x. So another way to write it, which I think is more intuitive on what you're doing, is f with a bigger parentheses, h, and then littler parentheses around that x, end of the bigger parentheses. So gotta go back up and remember what f of x and g of x are. H of x, I mean. I don't know if that one worked. Okay. Yeah, that didn't work. Sorry. I don't know how to get rid of it now with my there we go. Okay, we're just going to leave that there for now. I don't even know what it says. Sorry, f of x is sine of x and h of x is 2x. Sine of x and 2x. F of x is equal to sine of x and h of x is equal to 2x. And so f of h of x, which is 2x, which is 2x. So go in here, wherever you see an x, we're going to replace it with this 2x. So I have sine, I see an x there, so we're replacing it with 2x. Oops, 2x. But it wanted f of h of pi thirds. So it wants us to take now this pi thirds value, and we're going to plug it in wherever we see an x in this function. And so when we do that, we get back sine of 2 times pi thirds
Sorry, guys.
Okay, so I was changing this up from the book and they had pi 6 and I didn't want to do pi 6 because we had already done 60 degrees. No, pi 6 is 30. We had already done 30 degrees. So I changed it to pi thirds, not realizing that things had canceled before and would give us an angle we know. We do not know sine of 2 pi thirds yet. We're going to know that tomorrow. So I went a little, changing this up made it a problem that we don't know how to do quite yet in this class. So we will learn about reference angles. And then we'll be able to solve this. So sorry about that. Let's see. So kind of going back to angles. And with our angles, basically, we're going to make them look like triangles to help us solve and use trigonometry to help us solve certain angles. Just kind of remember, we are talking that an angle is in standard form if the initial side of that array was positioned facing towards the positive, on the x-axis, facing towards the positive direction. Remember, it was positive if we went counterclockwise. And so if you were asked to sketch um, 265 degrees. Okay, so since it's positive, I know I'm going counterclockwise, and then we're just going to kind of count around. We know that each axis, going from one axis to the other axis, is 90 degrees. And so this positive y axis is 90 degrees. We saw that whole, a line, that's 180 degrees. If we go to the negative direction of our y-axis, that's 270 degrees. And then here, if we didn't do any rotation, it's 0 degrees. But if we did a full rotation, that's the same as 360 degrees. 0 and 360, they're considered to be coterminal angles because their terminal side and is the same. So for 0 degrees, the terminal side and the initial side are the same. And then for 360 degrees, this terminal side of our angle is the same as 0. Okay, but anyways, so now let's go back and we'll get more into that in a second. 265 degrees. So if I start at 0 and I rotate, this is 90 degrees. I need to go further down to the negative x-axis, that's 180. Well, 265, that's a little shy, 5 degrees shy of this 270. So you're just gonna estimate it. And our angle would be right here. It's important that you're able to identify what quadrant our terminal side of our angle is lying. That is going to give us certain values for our trig functions. We'll talk about trig functions later representing x and y values. But recall you have quadrants, and the upper right hand quadrant was quadrant 1, upper left was quadrant 2, quadrant 3, and quadrant 4, going counterclockwise. And so this angle is going to be, oops, where did I sketch this? And so we know that 265 degrees, and I'm sorry, I wrote 270, but I was using the 270 to get to where my angle was. So that's really 265 is that angle. So theta, which is equal to 265 degrees, theta is contained in, so a little symbol that kind of looks like a capital E but rounded instead of, that means contained, is it contained in quadrant, so I'm going to pick a capital Q, 3. So the quadrants are in Roman numerals. Okay. So if it says sketch, let's say alpha. We haven't used that.
Professor,
Yeah.
I have a question. What did you say that symbol was next to the theta sign?
Yeah, so that symbol that kind of looks like a capital E that's rounded on the edges instead of boxed, this means contained in.
Okay.
So it's falling in that quadrant 3, that terminal sign.
Okay, thank you.
You're welcome. So let's sketch the angle. Alpha is equal to negative, I don't know, 125 degrees. And determine the quadrant. It lies in. Okay, so again, start at your standard position. And because it's giving us a negative angle, we're going clockwise. And so clockwise, that would make that negative y-axis. This is actually negative 90 degrees. Well, this is negative 180 if I'm going clockwise. And so 125 degrees, I know, well, that's, I think to myself, how much more is that from 90, which is 35 degrees. So I kind of approximate where I think it is. And so right here, this angle alpha is negative 125 degrees. So our angle alpha is contained in what quadrant? And so that one also falls in quadrant 3. So what is another angle that has the same terminal side as negative 125 degrees?
Professor, someone's having issues with the audio. They can't hear anything.
Okay. How about everybody else? Are you?
I couldn't. That happened to me earlier, and I ended it, and then I came back, and it worked again.
Okay, so then maybe we type that in.
Oh yeah.
Actually, someone type that in because I don't have.
I forgot. Log out.
Thank you for flagging me down because I didn't see that and I wouldn't have seen that. So that's a good question, and that's what we'll look at and start with on tomorrow. That's probably a good place to stop because we're almost over anyways. Let me just kind of tell you where we are. We were just jumping into 7.4 when I started to talk about coterminal angles. So today we've gotten through 7.3 pretty much. So remember, Wednesday's homework and Thursday's homework for your classes due on Monday by class time. So tomorrow's homework that's due is from Monday and Tuesday of this week. So your homework is 7.1 and 7.2. Has anyone gone to see the tutor yet?
I have.
Did you go see Amber or a tutor from the College Success Center?
Oh, I did the one from that started at 8 in the morning. I think it was a College Success Center.
Did it work okay?
Yeah, it worked good. I finished 7.1's homework assignment, so that's good. So I don't have that much. I only have 7.2 for tonight.
Awesome.
Okay.
Yay. So heads up, I got an email and I haven't checked out the problem yet, but there is one problem I think in 7.2 that one of the parts asks you to use a graphing calculator. And I'm not having you guys graph by graphing calculators. I'm not expecting you to know how to do that. So, so it sounds like it was number 21 in 7.2, and it's probably going to be 21 in yours too. It's just going to be that your numbers are going to be a little different than theirs. So skip that part that says use a graphing calculator to solve. Sometimes some of those that say use a graphing calculator, I actually would want you to know how to do, but I would let you know that. And I haven't looked at that problem exactly what it says. So just skip that portion that says use the graphing calculator. Let me pause.